Hello everyone. I'm continuing with my earlier class reactions involving CO bond fission. We have already done OH bond fission. Now these are chemical reactions of alcohols. So let us start. Alcohols, they give many different kinds of reactions because alcohol can behave as a nucleophile as well as an electrophile. Nucleophile, when it takes up the charge negative, that is OH bond fission takes place and RO minus develops, and or if there is bond fission of CO bond, that is the carbon takes up a positive charge, therefore it will behave as an electrolyte, electrophile. So let us see these reactions involving CO bond fission. I'll take some black color pen. So let us see C O H. Let us see if what happens when there is bond fission of C and O. There are different types of reaction that take place due to CO bond fission, that is when the alcohol behaves as an electrophile. That is, it will have a C plus charge. There are four types. The first one is using Lucas reagent. The second one is using phosphorus halides. Using phosphorus halides, we have already seen in haloalkanes. So I'll just brush up with it. Phosphorus halides. The third one is dehydration. The last one will be oxidation. Let us see this one by one. Pen. Just undo. Oxidation. Okay. On Lucas reagent, what is, first of all, let us see what is Lucas reagent. It is concentrated HCl along with anhydrous zinc chloride. Lucas reagent, I'll take another color pen. Let us take some examples. Now this is ROH. We have to do the fission over here. Lucas reagent will help us in doing this. Put down the Lucas reagent. Now HCl plus ZnCl2. So let us do the reaction. When we do the reaction, what we get is the H fission in between C and O. So the R and O bond will break. And this chlorine will get attached here. So this OH will leave as a good leaving group. So what we get is RCl plus the remaining H that is present in HCl will combine with OH and form H2O. So when an alcohol reacts in presence of Lucas reagent, that is HCl and zinc chloride, we get what is called as alkyl halide and water. I'll just put it down over here. This is alkyl halide. Few more reactions. This let us see whether it is 1 degree, 2 degree or 3 degree alcohol that is undergoing this kind of reaction. RCH2OH. So this is carbon attached to one carbon, that is 1 degree alcohol. Now this 1 degree alcohol, when we use, I'll just write down as LR, that is Lucas reagent. So from HCl, the H will get attached over here. H will be removed in the form of water, and the chlorine will take its place. So what we get is R So now what we get is R CH2 Cl. So plus along with water. So here this takes place at room temperature. CH2Cl is produced at room temperature. When we take, let us take another example. If I take R, that is 2 degree alcohol, This is 2-degree alcohol. The same thing, HCl plus ZnCl2. This leaves and the chlorine from here gets linked to this carbon. So what we obtain is RCH2, RCl plus H2O. This reaction takes place in 5 to 10 minutes. Within 5 to 10 minutes, this reaction takes place, and how we come to know that this reaction has taken place? By its turbidity. It will show turbidity on reaction. I'll take another reaction now. Let me take one tertiary alcohol. With the 2-degree alcohol, we have obtained a turbid solution in 5 to 10 minutes. Let us see with the tertiary alcohol. We can take this R group, same, or we can take it R, R prime, R double prime. Either the same alkyl groups or different we can take. Now the same thing again will happen, that is HCl plus ZnCl2. We are using Lucas reagent. So again water will be removed. With the help of this hydrogen, water will be removed. The chlorine will get linked to this carbon. So what we get is RCr RCl plus H2O. This will happen when we use tertiary alcohol, that is 3-degree alcohol, as well as it will take it won't take any time. This will happen instantly. Instant reaction. Instant reaction means in this the solution will turn turbid. Turbid it means it will look like but not exactly like buttermilk, but similar to that. Jelly kind of thing is called as turbid. So we will find a turbid solution here at room temperature. Even at room temperature also 1-degree alcohol will not produce any kind of turbidity, that is no reaction will be shown here. But 2-degree alcohol, within 5 to 10 minutes turbidity will be seen. But if we add 3-degree, that is tertiary alcohol with Lucas reagent, instant turbidity will be formed. So usually this Lucas reagent is used to find out the degree of alcohol. Next is chemical reactions involving CO bond fission with the help of phosphorus halide. When we use the reagent phosphorus halide, there are three, let us take chloride, trichloride, pentachloride and thionyl chloride. Let us see with this. Any alkyl group we can take. I will take C2H5 OH, that is ethyl alcohol. When I treat it with PCl3, that is phosphorus trichloride, what we get is similar kind of thing will happen here as it has taken place in LR. Same thing will happen over here. The OH group will be removed and one chlorine will replace it. So what we get is C2H5Cl plus we are having OH H3PO3. So what we get is H3PO3. Now these reactions with phosphorus halides are very important because point of view of our exams, they are very important. One of the reaction the second one is, we will come to it. Second reaction, same, I will take C2H5OH and treat it with phosphorus pentachloride PCl5. Here I have got the byproduct phosphorus acid. Now balancing it is not phosphorus. Balancing the reactions is not very important, as well as the byproducts are not important. But here when we are treating it with the halides of phosphorus or of sulfur, our byproducts are very important. Byproducts are important. Balancing is not very important. So let us do the reaction here. The same thing, the same case is repeated. OH group leaves. The chlorine gets linked over here. Only difference here, now let us see what is the difference here. We will form C2H5Cl plus POCl3, that is our oxychloride, plus HCl, that is our hydrogen chloride or hydrochloric acid. So only difference here is this is phosphorus acid is produced, and here we are making oxychloride. Phosphorus oxychloride. You write it down. Phosphorus oxychloride. Product here and the product here both are same, that is ethyl chloride is formed in both the places. Let us see the next one. One more reaction using halides. Let me take the same thing, C2H5OH plus, now I will take CSOCl2, that is thionyl chloride. This is thionyl chloride. Fumes of thionyl chloride, if inhaled, are very pungent, and we feel like as though we can choke. We can feel choked, although we do not die just because of the fumes, but we have very severe coughing due to thionyl chloride if the fumes are inhaled. So now this process, alcohol reacting with thionyl chloride, this process is also known as Darzon's process. We also call it as Darzon's process. Darzon's process. It is a very important process. The reason is, when we do the reaction from ethyl, we get the same thing, C2H5Cl. The OH is replaced by chlorine, plus SO is remaining, so we get SO2 plus we get HCl. Now SO2 is a gas and it escapes. As well as hydrochloric acid is a gas and it also escapes. So we are left with only pure ethyl chloride. Now due to this we have a good yield of ethyl chloride. That is why Darzon's process is used to produce alkyl halide. This is a preferred reaction compared to these halides. The next one, let us see dehydration. For doing dehydration, temperature is very, very important. I will just write down these two processes here once again. So the third process is dehydration. For dehydration, to remove water, we prefer using sulfuric acid or H3PO4. These two are very good acids when it comes to removal of water. Along with heat, different temperatures are used from 180, 140 to 170. Okay. Now let us do first, let us see the mechanism first, how dehydration of alcohol takes place. Process is very simple. When any alcohol treated with sulfuric acid at different temperatures, product will be formed. Different products will be formed. First, let us see the mechanism. C2H5OH. Let me take ethyl alcohol. Okay, I'll open it and write. I'll take this back country. CH3, CH2, OH. Okay. We know that there is a lone pair present over here. Now, this shift the page. I'll just shift the page a little over here. Now, this O, when we are doing dehydration, alcohol, it will pull the H plus ion from this sulfuric acid. From any mineral acid will give us H plus ions. So, this H plus ion will be pulled by the oxygen, the lone oxygen which is containing the lone pair. So, this now turns into H3C, CH2, O. This gets linked over here. So, I get one H here and this H as it is. The lone pair has now, since it has pulled the hydrogen towards it, the lone pairs have now turned to charge of plus. This is the first process in which we have done formation of protonated alcohol. We have added the proton, so it is known as protonated alcohol. This is the first. This dehydration mechanism will go like this. This is the first step. Let us do the second step. In the second step, we will have the formation of carbocation. Carbocation will be formed, that is CH3, CH2. We already have this protonated alcohol. H. This now will, since there are two H and O, therefore this O has become this molecule has become very unstable, due to which the bond breaks, and what we get now here is CH3, CH2 plus H2O. Now, since this is unstable, we get a charge of plus over here, carbocation. So, this is the form. The next third step, in the third step and that final step, there will be formation of alkene. Alkene is formed by alpha elimination. Let us see this CH3, CH2 we have got from the second step, that now on heating This is CH3. I'll erase it. I'll write it again. This CH3 that we have got, now it will be written, I will write it as like this, CH2, and one more H is there, which I'll write it here. Now, carbon next to this carbocation is known as alpha carbon. This is alpha carbon, so anything attached to alpha carbon will be alpha hydrogen. This alpha hydrogen will cleave, this alpha hydrogen will leave, and the bond will fall here with the removal of hydrogen. So now what we get is CH2 double bond CH2. So from alcohol we have obtained alkene. From alcohol we are obtaining alkene by doing dehydration. This is the first example that we saw. Now let us solve some examples using this mechanism. Let us solve some examples. Let me take C2H5OH only. Alcohol. In presence of H2SO4, that is H plus, we get H plus from this at 180 degrees centigrade. At 180 degrees centigrade, first we will get the formation of this kind of carbocation. All this will happen. The same thing will happen over here also. And next we will get the formation of carbocation CH3 CH2. So now I'll open it, I'll just write it like this. Instead of writing like this, I'll write it. CH3, I will put one H here and put one H here. So I'm writing it like this. This is CH3 and this is a CH2. So carbocation, when it is heated, what we get is alkene. What I'll get here is the bond collapses on this and we get CH2 double bond CH2. That is, we get an alkene. Now, if we treat this, this is ethyl alcohol. Let me take another kind of alcohol. 2 degree alcohol. Yes, let me take 2-degree alcohol. That is, I'll take this one. CH3, C, CH3, OH, reacted with sulfuric acid, the same thing. Here, instead of sulfuric acid, let me take H3PO4. And I take the same reaction, the same thing will occur. Now here, again the temperature is 440 Kelvin, or you can say 180 degrees centigrade, the same temperature. At the same temperature, this is 2-degree alcohol and this was 1-degree alcohol. When we take 2-degree alcohol, same type of reaction will take place. First of all, CH3, I'll keep it as it is. C, I'll write this instead of CH3, I will write it CH2 and H over here and OH as it is. Now this OH, due to protonation, we have lost the OH. So we have no more OH here. Instead of OH, we are now left out with a charge of plus over here. So a carbocation is formed. This step I have done over here. Now after forming a carbocation, I have to let go the hydrogen from the alpha carbon. So I can do it from this side or I can do it from this side, whichever side. Both are symmetric to it, both are neighbors to it. So I can do from any of the side. I'm doing from this side since I have already written like this. So what I'll do is, the bond hydrogen leaves, leaving its bond over here. So what I get finally is an alkene CH3, C, the double bond will be formed over here, CH2, 1, 2, 3, 4. So this is 1, 2, 3, propene. So 2-degree alcohol, that is 2-propanol, I have formed propene. Sometimes, one more reaction with the tertiary alcohols we will see. CH3, C, CH3, CH3, OH. This is 3-degree alcohol, that is tertiary alcohol. H3PO4 at a temperature. Now we will raise the temperature to 358 Kelvin. We will reduce the temperature to 358 Kelvin, or you can say 85 degrees centigrade. The temperature has been reduced drastically. Since it is 3-degree alcohol, the same type of carbocation will be formed. CH3, the carbocation will be formed next to the OH functional group over here. So C, CH3 and this CH3, I am putting it over here. So I got a carbocation over here. Now this this CH3, either this or this, any of them, all of them are attached to the mid carbon. I am changing the CH over here. CH2, H. So again the bond, this this hydrogen will leave, the bond over here will collapse here, and what we get is CH3, C, CH3, double bond, CH2, 1, 2, 3, 4. So what we get is propene, 1, 2, 3, propene again with the methyl group attached to it, or the 1, 2, that is 2 methyl propene. The last one, now 3-degree carbocation is always very stable. At low temperature also it is very stable, and therefore we get the reaction done at low temperatures. Since 3-degree carbons are very stable, and from 3-degree carbon if we are getting a carbocation, it is also very stable, therefore this reaction proceeds easily at low temperatures also. One more thing, if the reaction that we have done over here, we have got an alkene at 180 degrees centigrade, but if we take care that the temperature is maintained at 140 degrees centigrade instead of 180 degrees centigrade, if it is at 140 degrees centigrade, instead of producing an alkene, we will make an ether. We'll see this reaction, that kind of reaction later on. The last one is oxidation or oxidation dehydrogenation. That is cleavage of CH and OH bonds. Let us see this reaction. Here what we do is replace the hydrogens and introduce the double bonds. If we take 1 degree alcohol, mild oxidizing agent, 1 degree alcohol with mild oxidizing agent will produce an aldehyde first and then a carboxylic acid. We have already seen this reaction, but still I'll show it once again. Let us see. 1 degree alcohol RC, no, this is 2 degree alcohol. I'm sorry. Let us take 1 degree alcohol, RCH OH, 1, 2, 3, 4. I'll put H over here. Okay. This is an alcohol, alkyl alcohol. Now, if I use mild oxidizing agent, I'm doing oxidation, I'll use mild oxidizing agent or I can use strong oxidizing agent. Now, there are different mild oxidizing and strong oxidizing agents. Any of them we can use, like acidified KMnO4 or potassium dichromate. Acidified KMnO4 or K2Cr2O7, that is potassium dichromate, or we can use chromium anhydride in presence of water, along with water, or we can also use dichromate H2Cr O4, or we can That is anhydrous dichromate we can use, or we can also use chromium anhydride along with water. This is known as Jones reagent. Chromium anhydride along with water is known as Jones reagent. We can also use anhydrous chromium anhydride, but the reaction will not go further till carboxylic acid. It will behave as a mild oxidizing agent. So these are all strong oxidizing agents, and either of them we can use. Mild oxidizing agents are like PCC, that is pyridinium chlorochromate, or PDC, that is pyridinium dichromate, or anhydrous chromium anhydride, that is without water. This will behave as a mild oxidizing agent. If water is present, it will be strong oxidizing agent. So let us see the reaction with mild oxidizing agent as well as strong one. With the mild, oxidizing agent, when 1 degree alcohol, we get formation of aldehyde. Partial double bond is produced, made over here. Therefore, this hydrogen leaves, and what forms is R C double bond O H. That is, 2 hydrogen will leave, and we get the formation of an aldehyde. Now, if this aldehyde is further treated with a strong oxidizing agent, this was mild oxidizing agent, either PCC, PDC, or so on. If we use a strong oxidizing agent, strong oxidizing agent like KMnO4, acidified KMnO4, or potassium dichromate, or Jones reagent, what we obtain is a carboxylic acid, R C double bond O OH. So we get formation of carboxylic acid. If directly, instead of using mild oxidizing agent, we are using strong oxidizing agent here itself, instead of here, if we use it here itself, then there will be direct formation of carboxylic acid. It will not undergo so many steps. It will not undergo this step. Directly it will form carboxylic acid. When we use strong oxidizing agent. Similarly, with 2 degree alcohol, we will get direct formation of ketone. And here we have formed aldehyde. Here, if it is a 2 degree alcohol, this is 1 degree alcohol. If it is 2 degree alcohol, we will directly make ketone with strong oxidizing agent or mild oxidizing agent. Whether it is mild, whether either of them or either of this, both will give a ketone when it is 2 degree alcohol. But when it is 3 degree alcohol, no reaction will take place with either of the reagents. It does not react at normal temperature. If we give drastic conditions, definitely there will be a change. But otherwise, at normal temperatures, it won't do any kind of reaction. Now let us see oxidation by copper. In the same thing, we also have oxidation by copper. Now, oxidation by copper will take place at same temperature, but all the three alcohols will behave differently. I'll first put down all the three alcohols. RCH OH, that is CH2, RCH OH, and the last one is RCH ROH. Reaction with copper, 300 degrees centigrade. All of them I am doing with copper at 300 degrees centigrade. What I will get is removal of hydrogen. Removal of hydrogen, the hydrogen will be removed and a partial double bond will be formed in between this. So what I get is R C H O. If there is a partial double bond formation over here, then we lose the hydrogen from here. So two hydrogens are lost and we get the formation of an aldehyde in case of 1 degree. Let us see in case of 2 degree. In case of 2 degrees, same thing will happen again. This hydrogen is removed and there will be formation of a partial double bond character. Partial double bond will be formed in between. When a partial double bond is formed, this hydrogen will have to leave. So what we get is R C double bond O R 1, 2, 3, 4. So what we obtain is a ketone. This is an aldehyde. This is a ketone. The last one here 1, 2, 3, 4. There is no H. My mistake I have written here. There will be no H over here. For the reaction to take place, there is no H here. This is a 3 degree alcohol. When we come to reactions, oxidation reactions, whether it is mild or strong, we observe that if it is a tertiary alcohol, no reaction will take place. Now here, when copper is present at 300 degrees centigrade, dehydration will take place. Instead of this R group, I will take CH over here so that we can do the reaction and show. Erase this H, R, and instead I will put a C over here. You can take any methyl group or ethyl group, whichever you feel like. Now, this is a tertiary alcohol. This also is R, this is R, this is R. I haven't written as CH3, it is the same thing. So, at this time, Now here it is a 3-degree alcohol. Here what happens? This CH3, once again I'll open it and write it. I can write it as CH2 and H. This is CH3 as it is. So at 300 degrees centigrade, what happens is dehydration takes place. The hydrogen, this hydrogen leaves along with this OH group. So what actually is leaving? H2O. See here? There will be formation of water R C CH2 R. So now a carbocation has been formed. Wherever there is a formation of carbocation, the H will fall. H will fall at that carbocation. So I'll just erase this and write it again. Another H over here. CH2. There is a formation of carbocation over here. So this H will leave, giving its bond to the carbocation so that it gets satisfied. So what we obtain now is R, C, R. A double bond has been formed over here and C, H. CH, this was CH3, CH3. CH2 plus 1. No, I'm sorry here. This is CH2. And I get the formation of an alkene. I cannot show this kind of step over here properly because this is CH3, which I cannot I cannot go up to this step. Here itself, when this hydrogen is leaving, here itself a partial double bond is formed. So directly this double bond will be formed. Just erase this step. This is not correct. Here itself it will take place. When this HOH leaves, when this water leaves, at that time itself a partial double bond character has developed over here. So this has become C double bond O like this. I'll just erase this. We don't need so many steps. Directly we can form it here. R C double bond CH2 R, and what we get is H2O. Now we cannot like here you can see it is H2O, we are saying it is leaving, and a partial double bond is being formed over here. We cannot say the exact number like how it is taking place here. We cannot say that it has to happen. It is supposed to be a completely balanced reaction. Organic reaction, there are many molecules. Like for example, when we talk about physical chemistry, one molecule reacts, we say one molecule, it reacts with another molecule. And what we get is the third molecule. So 1 plus 1, we will say 2. That is, we are precise in saying that there is only one molecule of H and one molecule of O, and then finally we will get two molecules of H2O. We are very precise about it. But in organic chemistry, we cannot be so precise with our reactions, because when the reaction takes place, there are two reagents, both of them will react. So the quantity of one reagent reacting with another reagent may be same. So if it is same, we get exact product. RCH2 R double bond O. 1, 2, 3. Sorry. Now we have got this along with some byproduct. If this is some, now how many molecules? There are so many molecules. How many molecules have interacted and reacted with the other color molecule? We cannot be precise. And how much byproduct has been formed? That also we cannot be precise. It may be very small quantity, or the quantity may be more. But even if it is more, the presence of this byproduct does not bring about any change in the reaction. It behaves like a spectator. So spectators do not participate in any reaction. Therefore, in organic reactions, we do not consider the number or the byproducts. Neither we are concerned about the byproduct, nor we are concerned as to how many moles of byproducts are produced. Only we are concerned about our main product that we are obtaining by doing a certain kind of reaction. Now, tomorrow we will see phenols. Also the mechanism and ethers. How ethers are produced. How ethers are methods of preparation as well as reactions of ether. That's it for today. Thanks for joining me. Do join for my next class. Have a good night.